Hello everyone, let's talk about another medium problem on Leetcode today. Magic squares in grid, Leetcode 840. In this problem, we are given row into column grid of integers and then we have to count 3 into 3 contiguous magic square subgrids. A 3 into 3 magic square is a 3 into 3 grid filled with distinct numbers from 1 to 9 such that each row, column and both diagonals all have the same sum. Note while magic square can only contain numbers from 1 to 9, grid may contain numbers up to 15. Then they have given some examples as well. In example 1, we can see that this is the grid given to us. Then we will return 1 because we can find this 1 3 by 3 magic square here. And it is magic square because when we sum up the first row, we get 4 plus 3 plus 8, which is 15. Then when we sum up second row, we get 9 plus 5 plus 1, which is again 15. Then we sum up the third row, we get 2 plus 7 plus 6, which is also 15. Similarly, this diagonal, that is 4 plus 5 plus 6 is also 15. Similarly, sum of off-diagonal elements, that is 8 plus 5 plus 2 is also 15. Similarly, when we sum up the elements column-wise for each column, the sum will be 15. So this 3 by 3 grid was a magic square. But we have another 3 by 3 grid that starts from 3. And note that this is not a magic square. So if we sum up the elements, say for the first row, that is 3 plus 8 plus 4 will be 15. But if we sum up the elements diagonally, then it will be 3 plus 1 plus 2, that is 6. So the sums are not matching. So that's why this is not a magic square. So in total, we have only one magic square. Now let's jump into the solution space. In terms of solution, we have two methods that I will cover. One is the naive approach and another one is mathematical one. The naive approach is already the optimal approach, but mathematical approach is just for fun and learning. In the naive approach, we will go through the grid from top left corner, cell by cell, and check every subgrid that we can form during the iteration. But because we have to form 3 by 3 grid, we don't have to go through all rows and columns. But we will go till number of rows minus 2 for rows, because that will ensure that there are at least 2 rows below the starting row to make 3 by 3 matrix. Similarly, for columns, we will go till number of columns minus 2 because that will ensure there are at least 2 columns after the starting column to make 3 by 3 matrix. Then for every 3 by 3 square, we will check if it's a magic square or not. So here is the algorithm. Traverse the grid and extract all possible 3 by 3 subgrids. For each subgrid, check if it's a magic square, and we can do that by checking if it contains all distinct numbers from 1 to 9, and we verify if sum of rows, columns and diagonals are all equal to 15. And throughout the iteration, we will count the number of valid magic square subgrids. But why sum of elements in each row or column or diagonals in magic square is equal to 15? Let's see why. Suppose sum of the elements in first row is equal to x, and because it's a magic square, sum of the elements in row 2 or row 3 is also equal to x. Now let's add the sum from these three rows. So we will get 3x on the left side and it will be equal to sum of all the elements. And we know that in magic square we have elements from 1 to 9, and when we sum them up we get 45. Now 3x is equal to 45, so that is why x is equal to 15. And note that we don't have to check if sum is 15. What we can also do is we can calculate the sum of say first row, and then we can check if this sum is equal to sum of elements in different rows and columns. But I prefer using 15 here because then we don't have to introduce a new variable or anything. Now let's jump into the code part. So first thing we will do is we will start iterating on this grid to select 3 by 3 matrix. So let's define the dimensions. Let m be number of rows and n be number of columns. Let's also define count that we will return in the end. Now we can start iterating on this grid. For each cell, we will actually select a 3 by 3 grid and check if it's a magic square or not. So for that, we should loop till m minus 2. Or we can also do equality and then m minus 3. So it's up to you. And then similarly, we will do the same thing for columns as well. Now we will check if 3 by 3 grid starting from ij is a magic square or not. We can create a new function is magic square for that, and we can pass the grid and current rows and column to this function. And if subgrid is a magic square, then we will increment the count, and finally we will return the count in the end. Now let's define our is magic square function. It will be slightly tedious because we have to calculate each sums that is for 3 rows and then 3 columns, and also for 2 diagonals, and then check if all of them are equal to 15 or not. So first thing we will do is we have to ensure that the elements are distinct. So we can either use a hash set, or we can also use a Boolean array here because there are only 9 elements, and we can create this Boolean array of size 10. Then indexes 1 through 9 will represent numbers from 1 to 9. And each time we see a number, we will set the corresponding index in C into true. Now we will run a 3 by 3 loop to select the subgrid of size 3 by 3. And now our number will be equal to grid row, whatever row we have passed here, plus I. Similarly, column will be equal to whatever column we have passed, plus j. So suppose we have passed row equal to 0 and column equal to 0, then it will be 4, then we will go to 3, then we will go to 8, and then we will go to second row, so it will be 9, 5, 1. So this is how we will get a 3 by 3 grid. And now we will check if this number is less than 1, or if this number is greater than 9, or we have already seen this number, then we have to return false. And if that's not the case, then we will mark the number as seen. Now I can just copy this loop to save some typing. Now we will calculate the sum row wise and column wise and see if it's actually equal to 15. If it is not, then again we will return false. For each row, we will sum up all the 3 elements in it. We can select columns by doing column plus 1 and column plus 2. Actually, I can define int r is equal to row plus I, then I can actually use it here. Initially, I will be equal to 0. So we will pass in the first row, then I will become 1. So we will go to the second row, and similarly, we will go to the third row. And we are incrementing the column value because there are only 3 columns in this matrix. And if the sum is not equal to 15, that means we can return false. Similarly, we can actually do the same thing for column. So our column will be equal to int col is equal to col plus I. This should be C, otherwise we will have a name clash. Then we will add the values column wise. So for same column C, we will add the values at row plus 1 and row plus 2. And if their sum is not equal to 15 again, we will return false. Now we will do the same thing for diagonal. So for first diagonal, we will add the values at row plus 1 column plus 1 and row plus 2 column plus 2. And if the sum is not equal to 15, we will again return false. And finally, we will do the same thing for off diagonal. So we will take the value from first row and last column. So it will be row column plus 2, then row plus 1 column plus 1, and finally row plus 2. And we just select the column. So if this is also not equal to 15, we will return false. And finally, we will return true. Now let's run this code. Awesome. Let's submit this code. Okay, there's an index out of bound on line number 21. Ah, my bad. Because I should be doing or on if number is less than 1 or number is greater than 9. Because of the AND condition, this will always go there. And if number is more than 9, suppose 11 or something, then we will get index out of bound. So now let's submit this code. Cool. In terms of time complexity, it is O of m into n, where m is number of rows and n is number of columns, because we are looping from 0 to m minus 2 on rows and then 0 to n minus 2 on columns. So it will be m minus 2 into n minus 2, so roughly m into n. And is magic square is actually a constant time function. For example, here it will be O of 3 into 3, so O of 9, which is a constant. And similarly for these iterations as well, so it will be O of constant, so O of 1. And similarly, in terms of space complexity, we are just using the scene array, which is again 10 elements and is constant. So it will be O of 1 in this case. So this was naive approach. Now let's look at the mathematical approach. Let's look at some observations. First, we observe that center of the 3 by 3 magic square matrix is always 5. Let's prove it. So suppose our grid looks like A1, A2, A3, A4, A5, A6, A7, A8 and A9, and we have to derive A5 now. Then we can see that the middle element A5 can be part of 4 sums. So one column sums can be A2 plus A5 plus A8. Similarly, the row sum will be A4 plus A5 plus A6. The diagonal sum will be A1 plus A5 and A9. And finally, off diagonal sum will be A3 plus A5 plus A7, right? So now if we sum up all of these 4 sums, we will get 60 here because each of these sums is equal to 15. So 4 times 15 is equal to 60. This will be happening on the right side, and on the left side, we can sum up all the numbers, right? So we get all the numbers plus 3 times a into 5. So all the numbers we already saw sum up till 45. So we will get 45 plus 3 into a5 is equal to 60. So 3 into a5 is 15, and finally a5 is equal to 5. So our first observation is a5, that is our middle element, is always equal to 5. Now let's go to our second observation. Another observation is that in all the magic squares of size 3 by 3, the even numbers must be at the corners. So for example, in this magic square, we can see that 4, 8, 6 and 2 are at the corners. Similarly, all the odd numbers must be on the edge. For example, we can see that 3, 7, 1, 9 are on the edges, right? And finally, all the boundary elements, clockwise or counterclockwise, follow the order like 4, 3, 8, 1, 6, 7, 2, 9. Let's look at it. So it will be 4, 3, 8, 1, 6, 7, 2, 9. Similarly, here we can see that it starts from 4, 3, 8, 1, 6, 7, 2, 9. And similarly, we can check counterclockwise as well. So it will be 4, 3, 8, 1, 6, 7, 2, 9. And note that there are 8 possible arrangements of magic square of size 3 by 3, which you are seeing on the screen. And to see the proof of it, please refer the video from Mind Your Decisions, which I have shared in the description below. But for us, these observations are sufficient to solve this problem. So based on that, now we can actually tweak our is magic square function. So instead of computing all the sums, we can actually use these observations. So first thing we will check there is like if our middle element is equal to 5. So that is super easy. And second thing we will do is we will check if our boundary elements follow the pattern 4, 3, 8, 1, 6, 7, 2, 9. So for that, what we can do is we can actually run over this 3 by 3 matrix and get the boundary elements in clockwise order. So it will be 4, 3, 8, 1, 6, 7, 2, 9 for this one. Similarly, for this one, it will be 2, 9, 4, 3, 8, 1, 6, 7. So this is how we will actually get our boundary elements clockwise. And we saw that these boundary elements are rotated version of 4, 3, 8, 1, 6, 7, 2, 9. To find out if the string is rotated version of another string, what we can do is we can actually double the string and then check if the string is present in this double size string using the contains method. So for example, let's take this matrix. Then we can see that the boundary elements are 6, 7, 2, 9, 4, 3, 8, 1. And let's double the string 4, 3, 8, 1, 6, 7, 2, 9. Then we can check that 6, 7, 2, 9, 4, 3, 8, 1 exists in this concatenated string. So this is how we find out if one string is rotated version of another string. And there exists a problem on Leetcode named rotate a string, where we are actually given two strings and we have to check if one string is rotated version of another string. Similarly, for the counterclockwise, we have to reverse the strings. So if we look at it counterclockwise, it will be 4, 3, 8, 1, 6, 7, 2, 9, right? So we can actually take this string 4, 9, 2, 7, 6, 1, 8, 3 and again double it. And now suppose we have to find the pattern on this one. So again, we calculate the boundary string clockwise. So it will be 6, 1, 8, 3, 4, 9, 2, 7. So it will be 6, 1, 8, 3, 4, 9, 2, 7. So we will take these two strings, double them and check if the boundary conditions actually exist in any of these strings. And if yes, then this is a magic square. So now let's jump into the code part again. So now we have to just update our is magic square function, right? So first thing we will do is we will define those two sequences and we can define them in array of two strings. First sequence is 4, 3, 8, 1, 6, 7, 2, 9 and then we double it. Similarly, for reverse it will be 4, 9, 2, 7, 6, 1, 8, 3 and we again double it. And now we check if our middle element is 5. So we will do it by just doing it row plus 1, column plus 1 is not equal to 5. Then we will just return false here. Now only condition we have to check if the boundary elements follow the above two patterns. So we will get boundary elements as a string. To do that, so we will say get border string and we can pass grid, row and column. And now we can just loop over the magic sequence and check if magic sequence contains the boundary string. So if any of the magic sequences contain the border string, so that means this is a magic square. So we will return true. Otherwise, we will again return false. And now let's define get border string function. Again, pass these parameters to it. For efficiency reason, we can actually use string builder to store the boundary string. And now let's define two index arrays. So let's go here for that. Suppose we have to calculate the boundary index in clockwise direction from 4. So how will we do that? So let's define the row index first. So initial value will be 0 for row. Then row says 0, right? When we go from 4 to 3 to 8, so it will say 0, comma 0. There's no row change. Then we go to 1 here. So our row increases by 1. So here we will take 1. Then we go to 6 in row 2. So our row index also becomes 2. Then our row stays the same when we go from 6 to 7 to 2. So it will be 2, comma 2. And finally we come to 9. So that completes our boundary, right? So we will come to row number 1. Similarly, we have to do the same thing for column index. So again, we start from 4 in clockwise direction. So we go from 0th column to first column to second column. So it will be 0, 1, 2. Then we stay in the same column when we go from 8 to 1 to 6. So it will be 2, 2, right? Then we come to 7 in column 1 and 2 in column 0. So it will be 1, 0. And then we stay in 0 only when we come to 9. So now we have row index and column index. So now we will just loop over this row index and column index array. We can just use the same iterator because we have to make the change in both row and column at the same time. So it will be I less than 8, I plus plus. So now our row for the boundary element will be row plus row index. Similarly, column will be equal to column plus column index. And now we will append this element to the boundary string. And we will get the boundary string in the clockwise order. And then we will just return sb.toString. And now let's run this code. Because I'm using Python style array, that should be Java style. Let's run it again. Awesome. Let's submit this code. Cool. You notice that it's slightly slower, but overall the time complexity is still O of m into n. And maybe this whole string manipulation made it a bit slower, but overall time complexity is still O of m into n. Because its magic square function is still O of 1, and in terms of space complexity also it is O of 1. And anyways, we covered the mathematical solution for fun and learning. I hope this video was useful to you. If it was, please like and subscribe. Have a nice time. Thank you.